In the world of language generation, autoregressive models have long dominated, predicting one token at a time, left to right, in a rigid sequential dance. But a new contender has emerged, masked diffusion models, or MDMs. Unlike their autoregressive cousins, MDMs don't follow a fixed path. Instead, they learn to reconstruct sequences by iteratively denoising random fragments, unmasking tokens in any order, anywhere in the sequence. This freedom is powerful. It allows for non-autoregressive generation, parallelization, and the potential for smarter, more efficient reasoning. But here's the catch. The order in which you unmask tokens, your decoding path, has a massive impact on the final output. And yet, for years, this critical variable has been ignored. Most MDMs default to random unmasking, treating all paths as equally likely. Others use greedy heuristics, like unmasking the most confident token next, but these are short-sighted. A sequence of locally optimal decisions can still lead to a globally poor result. So why do MDMs consistently underperform compared to autoregressive models, despite their theoretical advantages? The answer lies in uncertainty. Not just any uncertainty, path uncertainty. We're the first to formalize this idea. The quality of a generated sequence isn't just about the model's capacity. It's about the cumulative predictive uncertainty along the entire decoding path. High uncertainty means the model is unsure, and that uncertainty compounds over time. Low uncertainty. That's a sign of a reliable, coherent path. To quantify this, we introduce denoising entropy, a novel, computable metric that captures the uncertainty of the generative process at every step. Denoising entropy comes in two parts. First, state entropy, the average Shannon entropy of the model's predictions across all masked positions at a given time. It measures how uncertain the model is right now. Then, path entropy, the integral of state entropy over the entire generation timeline. It's a global measure of how uncertain the model was throughout the entire journey from noise to final output. And here's the insight. Lower path entropy correlates strongly with higher output quality. We validate this empirically. Across thousands of unconditional generations, we observe a near-linear relationship. As path entropy decreases, so does perplexity, the standard proxy for text quality. More refined generation leads to more coherent, higher quality outputs. But this isn't just a diagnostic tool. It's a control signal. We propose two algorithms that leverage denoising entropy to actively guide the decoding process. First, entropy-based best of n, or EBON. Generate multiple independent decoding paths. Then post hoc select the one with the lowest path entropy. Simple, effective, and doesn't require real-time intervention. Second, entropy-guided sequential Monte Carlo, or E-SMC. A real-time active search strategy. Instead of blindly generating one path, we maintain a population of particles, partial sequences, each representing a potential decoding trajectory. At regular intervals, we evaluate each particle using state entropy. High entropy. That's a red flag. Low entropy. That's a promising path. We then resample, prune the uncertain ones, replicate the confident ones, and let the population evolve toward lower uncertainty. This is path-level optimization, not token-level greed. We're not just choosing the next best token. We're steering the entire process toward paths that are more consistent, more coherent, and more likely to yield high-quality results. And the results speak for themselves. On standard benchmarks like GSM 8K and Math 500, our methods boost accuracy, sometimes by over 4 percentage points, when applied to even the strongest baseline samplers. On planning tasks like Sudoku and Countdown, the gains are even more dramatic. E-SMC improves countdown accuracy from 36.3% to 44%, a 4.1-point jump. Why? Because solving these tasks requires a global, multi-step strategy. And only by evaluating the entire path can we identify the truly strong solutions. But the real breakthrough isn't just the performance gain. It's the principle. We've turned uncertainty from a liability into a key advantage. By quantifying path uncertainty with denoising entropy, we gain a principled, internal signal for guiding generation. We can now ask, is this path reliable? Is the model confident? Is it on the right track? And the answer isn't just yes or no, it's measurable. Theoretically, we justify this approach with 3 pillars. First, state entropy is a tight upper bound on the ideal, but intractable joint entropy of masked tokens. Second, it approximates the instantaneous training loss, meaning minimizing it aligns with the model's original objective. Third, and most importantly, the gap in expected path entropy between real and generated paths bounds the KL divergence between their distributions. That means, if we reduce the entropy gap, we're directly reducing the divergence from the true data manifold. We're not just making better outputs, we're making outputs that are closer to the truth. And this isn't just for small models. We scale our method to large MDMs like LLaDA and OpenDecoder, and the gains persist across reasoning, planning, and code generation tasks. Even more striking, EBON and E-SMC work as universal enhancers. Applied to any baseline strategy, uniform sampling, confidence-based, margin-based, or even advanced methods like PC Sampler, they improve performance. They're not replacements. They're upgrades. And they're efficient. With just 5 particles, E-SMC outperforms majority voting on Sudoku and Countdown. The entropy-guided approach uses the sampling budget more effectively than naive ensembling. So what's next? Denoising entropy isn't just a tool for better decoding. It's a foundation. It opens the door to calibrated decoding, uncertainty-aware reinforcement learning, and adaptive generation strategies that can dynamically adjust based on confidence. This work redefines how we think about generation in MDMs. We've moved from treating decoding as a random walk to viewing it as a search problem over a space of paths, where uncertainty is not a bug, it's a feature. We've shown that by measuring and guiding path uncertainty, we can unlock the true potential of masked diffusion models. The future of language generation isn't just about bigger models. It's about smarter paths. And now, thanks to denoising entropy, we finally have the tools to find them.